Welcome everyone. In this video I'm going to show you how to build a digital thermostat. So the brain of this digital thermostat is an STM32 microcontroller here. You can use an Arduino as well, because I wrote the source code in an Arduino IDE. So we can use the code on Arduino or STM32 Blue Pill, like in this case. You just have to change the pins because it is defined in a different way for STM32, but otherwise they are the same circuit from this perspective, from programming perspective, of course. So then this STM32 controls 4 different things. It takes care of the LCD here, it takes care of this rotary encoder here, which is also a switch, and then it takes care of this MCP41100 8-bit digital potentiometer, and finally it takes care of this NTC thermistor, which is attached to the surface of a TEC12706 Peltier cooler. So it will measure the cold side temperature of this Peltier cooler. And at the same time, to confirm the values, we have this thermometer here, which is a K-type thermocouple thermometer. It is attached also to the surface, quite close to the NTC, so it will measure roughly the same temperature. So we'll use the LCD to show some relevant information and see what is happening in the microcontroller. And then we will use this rotary encoder plus switch to change the target temperature, the temperature that we want to reach on the surface of the Peltier cooler, and to enable or disable the cooling, basically. And in this demonstration, the disabling will only mean that we stuck at that level where the Peltier cooler was set. So for example, if the cooling was set to 10 degrees, that required some certain power fed to the Peltier cooler, then when I will disable the cooling, that will not turn off the cooling, it will just disable the logic which checks the temperature and changes the power which is going to the Peltier cooler. But when I show you the code at the end of the video, I will also show you how to actually turn off by pressing this button. So you can turn off the cooling as well, but for this demonstration I just wanted to keep it constant after just pressing the button. So how do we control the temperature? And now comes the fun part. So previously, in the previous 2 videos, I was using this SZBK07 300 watt DC-DC buck converter. So what this does, it converts the input value or the input voltage to a certain output voltage based on the state of the potentiometers. And you have a CC, that's the current, and CV, that's the voltage potentiometer on this. And not on this because I removed it, but on its sibling, you can see it. So we have the 2 potentiometers, and based on that, we can change the output voltage. But for us, that's not enough, because we don't want to mess around with a screwdriver and things like that. And we want to change the values dynamically. And obviously, we don't want to sit over this all day long. So we want to make it automatic. So that's where the microcontroller and the digital potentiometer comes into the game. So what we do here is we have our NTC thermistor. So we measure the temperature with the STM32, and based on the logic that we set up in the program, we change the value of the digital potentiometer. And by changing the digital potentiometer, we will actually change the voltage across the CV potentiometer. So in this example, I actually removed this guy, the CV potentiometer, it is here, from the circuit, and then I just replaced it with the regular potentiometer, like this guy, and added a 10K resistor here. And then that's the point where the let's say, injected voltage comes from the digital potentiometer. So what we have is that we adjust the digital potentiometer, which will provide some voltage between 0 and 5 volts, and we inject that voltage through a 10 kilo ohm resistor into this circuit. So into the connection of the CV potentiometer. For more detailed explanation and information, check the corner up there, because I put the video there where I explain all this circuit in a very detail. Here I don't want to do that again. So then, based on our programmed logic, we change the potentiometer here, the digital one, and then we change the basically the feedback voltage which goes to this DC-DC converter. And based on the feedback voltage, we will get a different output voltage on the output side. So that is this side of the DC-DC converter. And that output voltage, now with these two wires, will go to the Peltier cooler. And then we get some temperature change in it. So then we keep measuring the temperature. And if we are not satisfied with the temperature, either we increase or decrease the feedback voltage, and then that will change the temperature of the Peltier cooler. And in my demonstration, I also defined a sort of tolerance. So we will try to keep the temperature within 0.5 degrees from the target temperature. And when we reached that, we don't really change the power, because we know that if we have that certain power provided for the Peltier cooler, then the surface, in this condition, of course, will stay at that temperature. And then when the conditions change, for example, we change the target temperature, or we have some thermal load on the cold side, or the hot side is too warm, then something will change in the microcontroller. For example, we cross a threshold or something like that, and then that will change the value of the voltage which is coming out from the voltage divider in the digital potentiometer. That will change the feedback voltage which is going here in this DC-DC converter, and change the characteristics of the Peltier cooler, or the parameters of the Peltier cooler again. So this is like an active feedback loop. So let's start up slowly, and before starting up this thing, I explain all these devices. So once again, this is a K-type thermocouple, and it is attached to the surface of the Peltier cooler. I'm just using a rubber band that provides sufficient tension, and it's not too thermally conductive, so that will be fine. And it's also very close to the NTC, so if everything is correctly set up, the two temperatures, one which is shown here and the other which will be shown on the LCD, should be close to each other, at least within 1 or 2 degrees. So this is discussed. Then we have the LCD. Once the parameters are shown, I will tell you what parameter is what. But basically we will see the temperature, the target temperature that we want to reach, and the parameters of the digital potentiometer. Then this multimeter will measure the output voltage. Here you see the clips. So this is the output voltage of the DC-DC converter. So that's the voltage which is applied on the Peltier cooler. And now I'm not measuring the current, I'm just measuring the voltage. I will tell you the current, what I see coming in this side from the power supply that I connected to the input of the DC-DC converter. But now we are not doing anything with the Peltier cooler other than just using it for the demonstration. So I don't really want to add one more device to measure the current. So that's done. And then this device is measuring these clips here, which are measuring the output voltage of this digital potentiometer. And then we came to this corner. This is a fan, so I try to sustain some small airflow here just to keep this heatsink cool, because if I stop moving the air here, the heatsink will start to increase the temperature, which will increase the whole Peltier cooler's temperature, also the cold side's temperature, and that will cause the programmed logic think that we are actually heating up the cold side by, for example, putting an object on it or something like that. Therefore, it will increase the power. But since there is no sufficient cooling on the heatsink here, the heatsink will also just go up in temperature as well as the cold side. So again, the microcontroller will think that we are still putting a thermal load on it, so it will increase the power which goes to the Peltier cooler again, and that will increase the temperature of the wall system again. So we will end up in a sort of an infinite loop and just heating up the wall device and probably destroying it. So to avoid that, I have some sort of active cooling. So I think I described most of the things, so I start to turn on the devices. So this will be our temperature measured on the top side of the Peltier cooler, which is the cold side. Then this will be the voltage, the output voltage of the DC-DC converter. And this will be the voltage which is coming out from the digital potentiometer. So the final part is turning on the microcontroller. So I just plug it in. So you see some random startup message, and then you see the details. So now, since we see the numbers, I can explain all of these things to you. So P, that's the value of the potentiometer, the variable which is changing between 0 and 255, and that is 0 now. Therefore, the output voltage, the nominal output voltage, is 0. And this says that the heating is disabled. So we are not controlling the DC-DC power supply, this guy here. And the temperature is 27 degrees, so you can see that we are 1 degrees within the temperature with the two devices. And then the ST is the set temperature, and now that is set to 30 degrees. Because what I do here, I assume that 30 degrees is our starting temperature, because the room temperature will not be higher than that. And then I also assume that the lowest temperature that I can reach on the surface of the Peltier cooler is, let's say, minus 25 degrees. So therefore I have like 55 degrees range between 30 and minus 25 degrees. And I divide that range into 255 equal parts. And that will give us the step in temperature and also in the output voltage of this digital potentiometer. So now we have everything arranged. You can see that now the output voltage of the digital potentiometer is 5 volts, and that's what I expect. So now I turn on the power supply which powers this thing, and we'll see how the things change, but nothing should start so far. The only thing is that the voltage should raise a little bit, because this cannot be 0 totally, but it's slightly above 0. So now we can see that, okay, this is half volt, this is 5 volt, and I turned on the power supply here, that is 12 volts. So now what I do, I set this set temperature to 15 degrees. And I enable the cooling. So I enable the cooling. So you can see that the P is increasing, and then the temperature started to drop, and the output voltage here started to increase, and now we are at 1 volt. So what is happening is that every 3 seconds we read the temperature, and then we compare the red temperature, here the T, with the ST. And if it's not within the threshold, or if it is larger, then we keep increasing the P value. And as long as these are not within a certain range, then we keep increasing the power which goes to the Peltier cooler. So you can see that now we increase the power, So actually the output voltage here from the potentiometer drops. So if the output voltage of the digital potentiometer drops, then that will cause an increase in the output voltage of the DC-DC converter, as you can see. So this goes up, this value, and this value goes down. And then that causes an increase. So you can see that if this value goes down, so basically I turn the potentiometer here digitally, then the power applied on this Peltier cooler will increase. And now you can see that we are actually within 0.5 degrees. So what should happen now is that the p-value should stay around this value, because now the thing sees, the microcontroller sees that, okay, we reached the set temperature, so now we just have to stay within the range that we defined in the beginning. So you can see that now we are, for example, at 47, and it is not changing at this moment. And as long as I don't do anything here, and we don't cross 15 degrees, then this will not increase. But I blow on this thing. So we gently blew on the surface, just some fresh air, and you can see that the power immediately went up, because the microcontroller thinks that we need more cooling power because the temperature is increasing. And I also made a small mistake, which is not too big mistake, but I haven't turned on the fan which cools the heatsink here, so that can also warm up the Peltier cooler as well. But as you can see now, it still works, but that higher temperature differences, so higher power to the Peltier cooler, the heating effect, the Joule effect is much higher, so I cannot have this cooling running passively. But now you see that we reached the set temperature, we are below it by a tiny fraction, and then the p-values stopped changing. And you can see that the two temperatures are basically the same. So we are measuring the good temperatures. And also this is just the nominal voltage, but it's comparable with the voltage that we can read in reality from the output of the potentiometer here. So now if I disable this, the p-value will stay on this level. So now I turn on the cooling because we will need it. So now we are blowing air on the heatsink here, and I go down to 10 degrees. And I enable the cooling. So again, every 3 seconds we check the temperature here on the surface. If it's not below the set temperature, we increase the power. And then 3 seconds later, we again check the temperature, the value of the T. And if it's higher than ST, we increase the power. And the increase is always just one increment of this P value, which is again between 0 and 255. So now you can see that the temperature is decreasing. So both on this and this device you can see roughly the same temperature, so they are quite identical. And you can see that the output voltage of the digital potentiometer drops. So now we are at around 3 volt. And you can also see that the temperature on the surface of the Peltier cooler is also decreasing. And also, if you observe it, then the steps are quite small. So it's like 20 something millivolts. So it will take some time, of course, to reach the maximum power, for example, because now we are barely halfway in the whole scale of this thing. And you can calculate the step size very easily. So you just take the range that this digital potentiometer covers, which is 5 volts. And you know that it is an 8-bit digital potentiometer, so 256 different levels are available. So you just divide your voltage range with the levels that you have, and that is roughly 0.02 volt. So now we reached the set temperature. So we are at 10 degrees on the surface of the Peltier cooler, and you can see that the p-value is not really increasing anymore. So these voltages for the power supply here and for the digital potentiometer, they are constant now. So you can see that this is very stable. So it stays at this temperature. So if you have a certain system with a certain load situation, which is, let's say, constant, then this p-value will not really fluctuate, because once you reached this temperature, you have a more or less constant environment, then you will always need the same power to maintain the same temperature. But then if you have some kind of fluctuations, disturbances in the system, like now, then you can see that the power will go up slowly. So now I just put my finger on the Peltier cooler's cold side, which increased its temperature. So then the system saw it that, okay, we should increase the power in order to go back below our set temperature. So now we increase the power, so the system is allowing more power to coming out from the DC-DC converter there, and that will cool back the cold side of this thing. But once everything settles down, the system will see that this is too much power, because we are going down below even maybe 9 degrees with this power. So then the system will start to decrease the p-value, so it will decrease the voltage which reaches the Peltier cooler. So now we reached our set temperature. So as long as there are no, let's say, negative effects, so something warm is coming here, then we will decrease the temperature here. So now it's slowly going under 9 degrees, 10 degrees, and eventually we will see that the p-value will decrease. So for example, if I could add another fan here to increase the cooling of this hot side, then I would probably be able to get the p-value a bit lower, because then the whole system's temperature, which also includes the hot side, would decrease, and therefore we would not need that much power on the Peltier cooler to keep the cold side cold. So there are some things that can be improved or modified, but you can see now that it goes quite nicely. So I think this was all regarding this demonstration. So we could see how the feedback works, and we could see that this works very nicely. We confirmed everything by using an external thermometer and also external voltmeters to see the different voltages, and you can see that we easily controlled everything by a rotary encoder. So what I will do now is I will go to my computer and I will show you how the source code works. So let's go to the computer and check what is happening inside this microcontroller. So let's quickly check the code. So since the digital potentiometer uses the SPI protocol to communicate with the Arduino or the STM32, we need that library, and you can see the pins for STM32 and Arduino as well. Since the only communication is going towards the potentiometer and nothing is being sent by the potentiometer towards the microcontroller, we are not using the other pin, so the master in slave out pin, because we just don't need it. Then we use the LCD. Again, you see the pins defined for STM32 and Arduino as well. Then we have to define a pin for the chip select, and in this case I'm using the pin A4. And for Arduino, the default pin is the pin number 10, but you can choose anything because this is just a pin which you need to change based on the communication going on between the STM32 and the digital potentiometer. Then we arrive to the variables. So we store the nominal voltage, that's the voltage calculated by the provided voltage for the digital potentiometer, and the value of the variable that we set for the 8-bit potentiometer. Then we have this set temperature, that is basically the goal temperature that we want to reach with the Peltier cooler. So now this starts at 30 and we go downwards. You can change this, it doesn't really matter. But if it is higher than the room temperature, then when you turn on the device, it might automatically start to cool, because you already have a set temperature below the measured temperature. Then we have a counter which keeps track of the number of clicks done with the rotary encoder, and this has a value between 0 and 255. So this is also like an 8-bit value, because it follows the 8-bit values of the digital potentiometer. And basically the value that we write on the digital potentiometer is this cooling power variable. So again, 0 to 255. And this will control the output voltage of the digital potentiometer, and therefore it will ultimately control the output voltage of the DC-DC converter. We can define a tolerance as well, and that is the tolerance for the temperature. So if the set temperature is within 0.5 degrees to the real temperature, we don't do anything. But if the real temperature is outside this range, so the set temperature plus minus 0.5 degrees, then we either increase or decrease the power on the DC-DC converter. Then we define another set of pins. These 3 pins are just the 3 different pins of the rotary encoder, and we need another pin for the AD converter, because we measure the voltage of a voltage divider made for the NTC thermistor, and the voltage is measured on the ADC 0 pin. We have another set of variables which are used to store the different statuses of the CRK and DT pins for the rotary encoder. Then we keep track of the time, because we want to have the code to run in a non-blocking mode. So we just enter the different kind of functions within the main loop at a certain time, and we don't get stuck in those functions if they don't have to run. So this is why we need this. Then we have a Boolean variable, whether the power supply is enabled or not. In this code, it means whether we write or update the value of the digital potentiometer or not. Then we need a bunch of variables for the NTC thermometer. So you can see that it has a lot of variables, but I don't really want to explain it because it takes a lot of time. Instead of that, you should check the upper right corner of the video, because I built this thermometer before and I have a video of it. So if you want to see why I have these parameters as they are, please check that video. So then we arrive to the setup part. So we first set up all the pins as inputs or outputs. So these are quite self-explanatory. Then we start our LCD and we just print some kind of message on it. Then we read the current statuses of the pins for the CRK and DT pins of the rotary encoder. Then we also define these 2 interrupt pins here. Actually, this is push button. I just copy pasted the line and then modified it to my other function, but now it's this comment is correct. So we see the change for the CRK pin, and we see, or we are looking for a falling edge with the push button. Then we notice down the time here. We also set the CS1 pin high. Then we start the SPI, because that is needed for the communication between the STM32 and the digital potentiometer. and we write a default value on the digital potentiometer. So we set it as 0. And you have to be careful because the potentiometer has, technically it has two inputs and then the Viper. And depending on which input you choose as the 5 volt and the ground, you can have 5 volt or 0 volt when you write 0 on the potentiometer. So you have to keep track of this. So basically you have to keep track of your connections, and then based on that and based on the purpose why you are connecting certain things. So in my case, the 0 value actually is the maximum voltage. You will see it on the schematics as well. So when we chose the 0 bit, then we have 5 volt on the output of the digital potentiometer. And then we start to increase this number, and eventually we will reach 255. Then the output of the digital potentiometer will be 0. And then we arrive to the main loop. So again, it's quite clean because I just put the function in them, and then we will see the functions later. But we check the time now too variable, and if 200 milliseconds elapsed, then we check the temperature, and then we print it and all the other relevant numbers on the LCD. And we update the time now 1, so we zero out the counter basically and wait another 200 milliseconds. And then we check another counter here, counter for time. So we check the system at every 2 seconds, and you have to keep in mind that your system, and by system I mean the cooling system, have a certain thermal inertia. So you have to size this delay to that, because so this time is very sensitive for your system. So if you have a system that picks up the temperature very quickly, then this number can be a short period of time. But if you have something like a big mass, I mean thermal mass, then you might want to adjust the temperature and the power less often, because if you want to update it too often, the system sees that let's say after 10 seconds we still haven't reached the target temperature, and it overpowers the Peltier cooler because it still thinks that you haven't reached the temperature because you just need more power, but in fact you just need maybe more time. So if you have a big system that you want to cool, you have to experiment with this time and see what is the good delay. But let's say we entered this, and let's say we have the power supply enabled. So we adjust the temperature. So we either increase or decrease the value of the digital potentiometer. And then we also write that value on the digital potentiometer. So then we reset the timer and we wait another 2 seconds, and we can enter this function again. So in the write potentiometer we don't have anything special. So the chip select pin has to go low, and then we can start our command. So first we send this number to the digital potentiometer, and then it is ready to receive the number which represents the value of the output. So that will be our cooling power value. And then we wait 100 microseconds and we put the chip select pin back to high. And here we can also calculate the nominal voltage. And as I said, we go the other way around with the voltage. So we start at 5, and if we increase the value of the potentiometer, we will decrease the output voltage of it. So here, that's why we have this 5 minus and then this term, because we start at 5. So if the cooling power is set to 0, then this term in the parentheses is 0. So the nominal voltage is 5 volts. But as long as we start to increase this, and for example we increase it to 256, then this term will be 5, because 256 divided by 256 times 5, so 1 times 5, that's 5. So then we reach 0 with the nominal voltage, and that's how it should work in my case. Then we have this adjust temperature function. It looks large, but it's very simple. So there are two if values, and maybe this can be improved to have more elegant layout. But so first we check if the absolute value of this difference, so the temperature that we measure and the set temperature, is smaller than the tolerance, so the difference between the set temperature and the real temperature is less than 0.5 degrees Celsius, we don't do anything. And by that I mean that we don't adjust the value of the digital potentiometer, so we don't adjust the power of the DC-DC converter. So the Peltier cooler will stay at the same level. But if we are not within the tolerance, then we have to see whether we are above the set temperature or below the set temperature. So if we are above the set temperature and we haven't reached the top of the values that we can pick with the digital potentiometer, then we increase the variable's value by 1. Otherwise, so if we are already at the highest power, we don't do anything. Or if this relation is the opposite, so that's the else part, so if the set temperature is larger than the temperature that we measured, and then if we still haven't reached the 0, then we decrease the power, because the set temperature is higher, so we overcooled the system basically, and therefore we can decrease the power, because we don't need that much power to keep our system at the set temperature. So basically this is the logic that decides whether to give more power to the Peltier cooler or decrease the power which goes to the Peltier cooler. So that's all. And then we have this convert to temperature function. Again, you can check the video what I made for this NTC thermometer, but what we do basically is we read the AD converter that will give us a voltage, and you have to keep in mind that there is a significant difference between Arduino and STM32. One is the resolution. By default, the STM32 has 12 bits and the Arduino Uno and Nano has 10 bits. So you have to keep that in mind, and also the reference voltages are different. One is 3.3 and the other is 5.0 volts for the two different systems. So based on the voltage, which is a voltage coming out from a 2 resistor voltage divider, we can calculate the resistance of the NTC, and based on the resistance and this formula we can express the temperature in Kelvin, and then we just convert the Kelvin to Celsius degrees, and later on we will use this value for some other calculations. Then we have this function which is triggered by one of the interrupt pins, that is the CRK. So we read the CRK and put it in a variable, and then we see how it's related to the previous state of the CRK pin. And based on that we also read the DT pin, and we see the relationship between them. And why we should do this? Because we are basically comparing two signals or changes of the states of two signals, and based on the relationship between these two changes we can see whether we rotated in clockwise or counterclockwise direction. So based on that, either we increase the value of the counter or we decrease the value of the counter. And again, we have a restriction, so we can only move in between 0 and 256. So this part only works if we are below 256, and this part only works if we are above 0. So then if we enter, as I said, we increase the counter and we also recalculate the set temperature. So then here we will see that the set temperature is 30 that we set up in the beginning of the code. So this is our initial temperature minus 55 times the counter divided by 255. And what we do here is that the 55 comes from the range that we assumed to use. So basically we assume that our highest temperature is 30 degrees and the lowest temperature that we can reach on the surface of the Peltier cooler is minus 25 degrees. So this is in total, the difference between these two numbers is 55. So that's what we do here. And at the end, when the counter will be 255, then this term in the parentheses becomes 55. So then that means that the set temperature is at the lowest temperature, minus 25 degrees. And also, we can see from here that if we have the counter as 1, then 1 divided by 255 times 55, and that's 0.21. And 0.21 is basically the steps for the temperature. So if everything is very ideal and very precise, then we have 0.21 degrees precision for the temperature. So then the other part of the encoder part is when we are rotating in the other direction, so we decrease the value of the counter variable. So that happens here, and obviously if we reached already 0, then we don't do anything. And then we also take care of the push button on the rotary encoder. So if the power supply enabled variable is false, or was false, then we just change its state. I know that this can be programmed in a more easy way, using the exclamation mark and so on, but if I'm explaining to someone, this is more easy. It's more easy to see through the code. So then here we set the power supply to enabled. So when we go back to the main part, the code will enter this part if we enable the power supply. And here we put this variable to false. So that means that this part will not run anymore. But if this part doesn't run anymore, we don't write the potentiometer. So the potentiometer will still have the last value of the cooling power variable, because that's what controls the potentiometer. So if we are here, then what we should do here is first we have to write this variable to 0, and then we disable the power supply. And maybe we have to restructure the code for that, but you have to keep in mind that first you might want to reset this variable to 0, so you basically shut down the power for the Peltier cooler, and then disable the code as well. So this is up to you how you want, but when I just disable, I just want to disable the change in the power output. And then we have this print LCD. I don't really want to explain all the things because you can literally read it, so I just explain this part. So we have the very first position in the 16:2 LCD, and then we write this text there. Then we move the cursor after this text, so literally here where we have the cursor in the editor, and then we first delete the screen, but then the cursor will end up here, so we move back, so this is why we have this line. We move back here after this symbol here, and then we update the cooling power value. And after that we move to the 6, so we have some gap between 2 and 6, and that is the space for this number. And then to the 6 position we print this, and again we have a small movement because this was the 6th position, so 7 and 8. So we move to the 8, we delete the screen again, we move back to the beginning, so here or here, and then we print the nominal voltage. And then based on the PSU enabled, either we write enabled or disabled. And then here we do the same as we did here, but with different variables and letters. And in the end of this code, we just have some maybe useful thoughts or useful ideas. So here you can see how I calculated the resolution in temperature, and how you can calculate the ohmic resistance of the digital potentiometer if you need it for some reason. So yeah, this was the code, and I think it was not so complicated. The only thing that you have to really make sure and maybe code yourself, I just don't want to code that right now because it was not really necessary for the demonstration, that when you disable the power here, you might also want to reset the value of the potentiometer. So what you might want to do is basically you want to put this here. So if we have this function here, it is maybe more smart, because then what we can do is that if this is 0, then we always write 0. And then we need to have the power enabled in order to adjust the temperature. And basically, when we adjust the temperature, then we change the value of the number which is passed to this function here, and finally passed to the digital potentiometer. So then, when this function is not working anymore, we still changed the cooling power within this interrupt function. And whatever is happening to this part of the code, the right potentiometer function will always run, because that doesn't depend on this. So therefore, since we updated this here, the next time when the 2 seconds are elapsed, we enter this function and the cooling power will be 0 now. So we modified the value of the digital potentiometer, and actually we turned off the power. So now I modified the code and showed you how to do it nicely. So in this case, when you have this, you also turn off the power supply basically, or put it to the minimum voltage after clicking the button and disabling the power output. So yeah, this is also done. So everything is done. I hope that this video was useful or helpful to you. I talked to you in the comment section, and some of you were very interested in this. So I hope especially you guys will appreciate this code, and you will find it helpful. Obviously, if you found some mistakes or you can improve any parts of the code, please let me know in the comment section, because yeah, I'm also learning this, so we are learning this together. So any kind of comments are appreciated, so thank you for that. And you should visit my website, curiousscientist.tech, and also check the description, because in the description you will find all the relevant links and things. For example, you can get the schematics and so on, so that can be useful to you. Please don't forget to subscribe my channel, that helps me a lot. You can also donate me if you want, so I can buy new parts and demonstrate them or make some tutorials based on them, and so on. So I hope that this video was useful, and see you in the next video.